only in a very heuristic fashion. And this time let us look at the fully developed flow, where we said that the flow profile should not change, they look identical. That means you can superpose one on the top of the other with distance. Okay. So, fully developed flow. Okay. Now, in the fully developed flow, I am writing the full-fledged Navier-Stokes equation once again. That is where we will start, and we will show that what are the terms that we can actually neglect. So, we will follow the scaling argument here, and we will try to show that how we can get to the revised version. Okay. So, here x scales as L as before, y scales as however d, because the boundary layers have already merged. So, the scale of y is basically d, and u, the scale of u is basically u, that is the, because we saw it is only 1.5 times the maximum velocity. So, it should be, the scale is still the same. Okay. We are not going up by one order. Okay. So, of course, using this from the continuity equation, you have u by L, okay, should be the same as v by d, right. This gives rise to v being equal to u by d by L, okay, where L is much greater than d, correct. So, if that is the case, that when L is much greater than d, okay, you can take v to be almost equal to 0, okay, in this particular case. So, therefore, du by dx is equal to 0, right, okay, du by dx equal to 0. Therefore, this leads to that u is not a function of x anymore, right. You understood the steps. So, we went from the continuity equation, there we showed that v is almost equal to 0, because here L, the length at which you are taking your entrance, this long pipe basically is much greater than d. As a result of that, moment v becomes equal to 0, then by mandate du by dx also has to be equal to 0. So, that would mean that u is not a function of x anymore. Okay. It can be a function of y, it can be a function of any other things, right, but it cannot be a function of x at this particular point, right. So, the momentum equation then becomes very simple, right, because if you look at the momentum equation, the first term vanishes because du by dx is not a function of x anymore, and the second term vanishes because v is equal to 0, right. Okay. So, and if you look at these two terms now in the momentum equation, that is del square u dx square and y square, of course, we know that x scales as L and y scales as d, L being much larger than d. So, then naturally only one component survives, which is this one, this goes to 0, right, because it is L square, right. So, the momentum equation basically, if we write it, vanishes and becomes something like this, dp by dx equal to gamma after all these manipulations, right. Only two terms survives, this one and this one, that is it, right. So, that would be an interesting proposition. When you look at the momentum equation in this particular form, you will find that the flow is obviously moving, but it is a non-accelerating flow, because the convective derivative, which is the convective part, has gone equal to 0. Okay. So, there is no convection, no convective derivative, let us not say convection, no convective derivative or no convective acceleration, that is equal to 0, right. So, the flow is basically happening due to a balance of pressure and viscosity. So, shear is balanced by the pressure, that is what you have, right, shear and pressure, correct, and it is a non-accelerating flow. This part should be very clear that this is only valid in the fully developed regime. Now, Now that we have this particular equation, we don't need boundary layers anymore. I mean, we don't need scaling arguments anymore. We can simply solve the equation from the first principles, right? So we can write the boundary conditions first. As we write the boundary conditions, so let's take this as x, this as y, this being the axis, right? You can have it in any other way that you want, doesn't matter, right? So u is equal to 0 at y equal to plus minus d by 2. The simple reason is that these are walls, so the no slip condition applies, no slip. Okay. The equation also can be integrated, okay, very easily. So du dy is equal to 1 by mu dp dx into y plus c1. That's the first part of the integral, and then you integrate it once again, 1 over mu dp by dx y square by 2 plus c1 y plus c2. Okay. So u is equal to 0 at y equal to d by 2. Okay. Using that, so u is equal to 0 at y equal to d by 2. Then you have 1 by mu dp by dx d square by 8 plus c1 in by d by 2 plus c2 is equal to 0. Okay. So that is the first one. Okay. So in this particular case, as you can see, so this is the full expression that you get. Now u is also equal to 0 at y equal to minus d by 2. Okay. So in that particular way, you will have 1 over mu dp by dx d square by 8 minus c1 by d by 2 plus c2 is equal to 0. Okay. So this is the second form that you have. So there is one more thing that we can apply, that if you look at the velocity profile, it is symmetric, right? It is a symmetric velocity profile because on both sides. So there has to be an inflection point right at the center, which would mean that your du by dy has to be equal to at y equal to 0 has to be equal to 0 in essence, because the slope has to vanish, right? So if you look at this from here, you will get your c1 is equal to 0, right, because the slope will vanish, right? And from the other part, you can get c2 is equal to minus 1 over mu dp by dx d square by 8, right. So that will be the other part. So c1 is equal to 0, c2 is equal to that. Okay. Now if you so your total u therefore becomes mu dp by dx y square by 2 minus 1 over mu dp by dx d square by 8, or u is equal to minus 1 over 8 mu dp by dx d square 1 minus y by d by 2 square. Okay, got it? This can be further represented as something like 3 by 2 u (1 minus y by d by 2 square), where this u is written as d square by 12 mu minus dp by dx, right. There is only one pressure gradient, so you can write it instead of partial, you can write it as an ordinary differential as well. Okay. So as you can see, so therefore your final expression for u becomes 3 by 2 u minus y by d by 2 square. That is the final expression that you have, where your u is given in that particular functional form, right. Similarly, your f, which is your friction factor, which is tau y wall by rho u square, can be also evaluated. Okay. So tau wall, you can easily evaluate it as mu into du by dy at the wall, okay, and you can divide it by rho u square. So all these expressions you can find out, okay, find out quite easily. Okay. Now, let us talk about for a round pipe. So, this is for a duct, right, two parallel plates. For a round pipe, the essential expression is still the same, given by 2u into 1 minus r by r naught square in that case, where this u is basically, this is small u by the way, okay, is r naught square by 8 mu into minus dp by dx, right. So, it is a round pipe like this. This is r naught, which is the radius of the pipe, right. So, it is very similar expression. Okay. This time you have to take care of it by using the polar coordinates in this particular case, right. Okay. So, so what did we do? We found that indeed the u, the fundamental takeaway things, u is not a function of x. That was the first point that we took. Second point was that flow is non-accelerating, right. It is a balance between shear and pressure. Got it? Okay. And there is an exact solution that exists, which is given by this. That would be your fourth point, right. There is an exact solution. That means you know in the fully developed regime. Why did we get away? Because the nonlinear term of the momentum equation got cancelled because there was no convective derivative to begin with, right. So, taking advantage of that, we were able to now get to this particular situation where the flow velocity actually there was no acceleration term. So, therefore, it offered an exact solution of this particular problem, and that is exactly what we did in here. Okay. But however, few things to note in the developing region, obviously, okay, this is not true. Okay. The flow is accelerating in that particular reference frame. U is not a function of fx only, u is not a function of fx, that statement does not hold water. Okay. And so, therefore, there you have to solve the whole momentum equation, which is what we did in our integral approach, right. Okay. So, you can see over here that once the flow becomes hydrodynamically fully developed, it has got an exact solution. That means in the energy equation, where you have basically ut dt by dy and terms like that, it can be easily applied. This u can now be taken and easily applied over there, right. You do not have to, you can solve it a priori, and you can take that solution and you can apply it in the momentum equation, in the energy equation, provided that you are operating in the fully developed regime of both the cases. That means you are in the hydrodynamically fully developed regime, and of course the temperature or the energy equation is also in the thermally fully developed regime. Okay. So, it can be the situation, at least the flow has to be hydrodynamically fully developed in order to apply that u and directly place it over here. Okay. So, that is what we have done, and for the round pipe we have seen that we have given an expression for the round pipe as well. Okay. Now, let us see that for temperature, what are the key concepts that one needs to learn, okay, before one takes up this particular problem. Okay. So, let us introduce the concept of mean temperature. In fully developed flow. What do we mean by that? Okay. So, let us take a pipe, round pipe. As I said, round pipe and ducts, they are not very different. Okay. This is of course the center line. This is of course R naught. Theta is obviously in this direction. So, it is theta symmetric. So, this way is x, that way is r. right? Okay. So there is of course an m dot amount of fluid that is flowing through this particular pipe. There is a net heat transfer that is happening from the wall into the fluid, okay, as it passes through this pipe, and particularly we are interested in this small segment that you see over here, okay. That is what we are most interested in. So we apply first law, the first law of thermodynamics, okay, over here. So we say that q double prime, just look at the expression, 2 pi r naught into dx, that is the dx is this elemental section, right. So this is the total amount of heat that is dumped into that elemental section dx, leading to m dot, okay. So the m dot is a mass flux that was coming in. So the enthalpy of the fluid should have increased in this particular fashion. So whatever is coming out on the other side should have a little bit more enthalpy than whatever is entering. That is because of the amount of heat that you have actually supplied, right, okay. Now for ideal gas, okay, dH is given by Cp dTm, okay, where we are introducing Tm as the mean temperature, and we will see what this is in a second, mean temperature, okay. So Tm is basically the bulk temperature of the fluid entering the control volume. This is a control volume, so the bulk temperature of the fluid that is entering inside into the control volume is given by Tm, okay. So all the whatever may be the temperature distribution of the fluid doesn't matter, it is the average temperature at that particular section. In this particular section, whatever was the average temperature, that is what we have taken, okay. That is your Tm. So this Tm changes by a little bit because you are dumping more amount of heat, right. There is a fluid which is coming with a mean temperature, you have dumped x calories or joules of heat into the fluid, that naturally the mean temperature will rise a little bit, right. As a result of that, the enthalpy of the fluid also changes by that little bit. So that enthalpy is given by dH is equal to Cp into dTm. That is, a change in enthalpy is linked to the change in the mean temperature, okay. So normally your temperature T would be a function of both x and r, right, because it will be a function and it is theta symmetric, okay. So therefore there is no variation with respect to theta, but with respect to x and r there would be a variation of the temperature, right. So basically your Tm is the representation of bulk, or in other words average temperature, okay, bulk at the average temperature that accounts for R variation. Understand what is R variation? That means the variation across the radial direction, okay, at fixed x, okay. So at any fixed x, if you average out over R, the temperature that you are going to get is basically your Tm, okay. So you have q double prime 2 pi r naught into dx equal to m dot Cp dTm, okay, m dot Cp into dTm, okay. Now what will be your m dot in this particular case? M dot can be represented by that average axial velocity that you have, that we just derived a few moments earlier. So this can be written as rho u into A, okay, into Cp into dTm, got it, okay, rho um Cp into dTm, or in other words you get dTm by dx is given by 2q double prime divided by r naught rho Cpu, okay. So this is the average axial velocity, that we already derived earlier. That u, remember that in the velocity profile, if you have forgotten, okay, we already had an expression for u, right? U was 2u to 1 minus r by r naught square. Do you recall that? Okay. So, this is nothing but that average velocity that we are concerned with here. Now, so you can see that for example, even in this particular expression, you know that the u is maximum at the center, right. So, when you actually put r equal to 0, okay, u becomes equal to 2u, that means twice the average velocity, right. Now, this is the average axial velocity, therefore, that is what we have used over there. Remember, we said that we are going to use the momentum equation as much as we can, right. So, this establishes one fundamental relationship between dTm, that means the mean temperature, and the corresponding velocity and the heat flux. This establishes that, and how the mean temperature varies. Now, what is the relationship still between T and Tm, right? That is what we are going to do before we end this lecture. T and Tm, right? We said that T varies with x and r. Tm is basically takes into account that r variation at fixed x, right. So, there must be a relationship between Tm and x, okay, which we need to establish. Okay. So, that is what we are going to do. So, the relationship between Tm and T over here, if you write this expression once again in the proper form, okay, what you will get, this area integral Cp T dA, right. That is a total change if you take into account the temperature. This is the actual temperature, which is a function of both x and r, right. So, you are integrating it across the area, that means across the cross sectional area. Okay. So, there you have both u, this u is the fundamental variable, this is not the average, and this T is also the native, the temperature, or the temperature at each point, right. So, based on this expression, also we know that 2 pi r naught dx is given by rho u d Cp dTm, that is also we have just derived. So, therefore, rho u a Cp dTm is equal to d, the area integral rho u Cp T dA. Got it? Just we are just replacing the temperature with that. Okay. So, in other words, or rho u a Cp Tm, basically have to integrate it over the two variables rho u Cp T r dr d theta, right. This is the area, right, or in other words, this will be u pi r naught square. For this is the average area, I mean this is the area, not the average area, okay, into Tm, okay, is equal to 0 to 2 pi 0 to r naught u T r dr d theta, or Tm is equal to pi r naught square by u 2 pi 0 to r naught u T r dr d theta, right. So, this is the expression that you get links Tm with the corresponding T, right, and H, that is the heat transfer coefficient in all these flows, will be given by Q double prime into T naught minus Tm, right. Okay. That will be the case for all the cases that we are going to do here. Okay. So, basic point is that we require T in order to calculate Tm, otherwise you cannot calculate H. So, the problem is not gone, you have just transferred the problem to a new variable, which is Tm, which is nothing but it is more like an integral approach, where we have basically integrated out the whole thing, right, okay, in a way that it is understandable, right. And so, we have shown that how the mean bulk temperature is related to the actual temperature, and we have also cast that the heat transfer coefficient perhaps can be written in terms of the mean temperature, only in this particular case. Okay. So, in the next class we will see what is the nature of this Tm, how does it vary, okay, with distance and with different conditions, uniform heat flux or uniform surface temperatures. That we will do in the next class. Thank you. We actually developed the concept of mean temperature in a fully developed flow, right. So, mean temperature was a useful quantity because it was a radially averaged temperature essentially. So, the temperature was averaged in the radial direction, and we introduced the concept of mean temperature, and we wrote this particular equation. If you look at the presentation, R naught rho Cp into U, where U was the average axial velocity, correct, okay, and Q double prime was the heat transfer or the net heat transfer from wall to the fluid. That was a concept that we developed. We also found that while developing this concept, okay, we found that Tm, which is the mean temperature, is actually given by this. We did last class. So, I am just noting down the key quantities U, Tr, dr, d theta. This U is basically the local velocity, T is basically the temperature field, right. So, T in general is a function of both x comma r, right, whereas your mean temperature should be a function of x only, because we are taking care of the r variation away, right, because that is what the integral, the purpose of the integral exactly is. Okay. So, also we defined H, which is basically the heat transfer coefficient, is basically T naught minus Tm, okay, where T naught was basically the wall temperature. Okay. So, that was the whole exercise that we did in the last class, where we defined these three important quantities, and from here we thought that the temperature we have to find it in some way. So, our motto is to basically find what is this temperature field x comma r in the fully developed regime. Like for example, in the case of velocity, okay, we found that in the fully developed regime the velocity u, okay, was a function of r only, right, okay, and it was not a function of x. This we found in the fully developed regime, right, in the fully developed regime. What about t? The question remains, what about t, whether t is also a function of x, is a function of r, or is only a function of r, and things like that, right. That is what we need to answer, okay, because based on that we can find out what your Tm is going to be. Once we find Tm, the all important quantity once again is the heat transfer coefficient, which is a function of Tm in this particular case, right. So, all these things are kind of coupled with each other. So, T is needed, okay. So, let us take the formulation based on a round pipe. So, our basic problem is therefore a round pipe, okay. So, the equations will be a little different, okay, from the Cartesian coordinates. Is basically theta symmetric, okay, no variation in the theta direction, and it is fully developed, okay, both in terms of temperature and velocity. Of course, we do not know what the fully developed temperature profile is going to look like. That is what we are going to find out. Velocity profile is already known. That is what we did in the last class, right. Now, fully developed means that even the thermal boundary layer, okay, I am not saying that the two boundary layers have the same entrance length. That is not the question over here. So, if this is the round pipe that you have, this is the center line, it is possible that this is your XH, which is the hydrodynamic boundary layer merged, okay. So, from here onwards X greater than XH is what we call hydrodynamically fully developed, right, whereas okay, the temperature profile may be something like this, okay, or it can be also something like that, okay, whatever, depending on whatever is your Prandtl number is. This, say, call it xt. So, if x is greater than xt, okay, we call it thermally fully developed. Okay. So, if x is greater than xt, we call it thermally fully developed. If x is greater than xh, we call it hydrodynamically fully developed, the two boundary layers over here. Okay. So, we are in a regime in which x is greater than both xh and xt. That means we are somewhere here. Okay. So, that will be like your velocity profile, which you already know, parabolic, and we want to know what is the temperature profile here, right. So, that is the unanswered question that we have. Okay. So, let us write down the governing equation, because we already know the momentum equation, because the velocity is a known variable over here. We just go on to the energy equation at this particular point. So, the energy equation, u dt dx plus v dt dr alpha t dr square plus 1 by r dt by dr plus del square t by del x square. This is the full energy equation written in polar coordinate systems, right. And of course, we know u is only a function of fr, and we know v is equal to 0, right. These two things are already pre-known, right. So, what you can write, okay, by simplifying this equation, so it will be alpha dt by dx is equal to delta square r square plus, okay, 1 by r dt by dr plus t dx square, right. Okay. So, that will be the combined equation after we take off this particular term, right, and we write ur as a u as a function of ur only. Okay. Now, there are three main terms in this particular equation, right. So, this is what we call the axial convection, right. This is the axial convection, right. This is what we can call it to be radial diffusion or conduction, okay, and this one is called axial conduction. So, there are the different modes, right. So, you have the axial convection, then you have the radial diffusion, and then you have the axial conduction. The idea of framing this equation now is that we have to find out which terms are important, which terms we can safely leave out. Okay. Obviously, we have to show some legitimate reasons why we are actually deleting some of the terms. So, let us do an exercise in scaling once again, and let us see whether that makes sense in this particular context or not. Okay. So, let us take it term by term once again. Okay. So, what about dt by dx, right. dt by dx is nothing but q double prime divided by rho Cp u into d, right. Okay. And d square t by dx square is basically q double prime rho Cp u into d, that x factor comes into the picture. Let us put this very nicely. Okay. 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 So, the first, so we know dt by dx and we know del square t by dx square, right. These terms will be known right now. Okay. And of course, there will be the last term, which is basically dt d square t by dr square, right. Now, that will be given as delta t, right, divided by d square, because we already know that r has reached d, that means the center of the pipe, right. So, basically this comes because of the fact that thermal diffusion has reached the center line. Got it? Okay. So, let us now take term by term. So, the first term will be u by alpha q double prime rho Cp u d, okay. That is the first term. This should be delta t by d square, right. So, that is basically the radial term, the radial diffusion terms, right, okay. And you have 1 by x q double prime rho Cp u into d, right. That is the axial conduction term, right. Now, pay attention, this how we got this, because we used the corresponding formulation. If you remember that how we found out the dt by dm kind of a term, okay, it comes readily from there. You recall the term, right, that dtm by dx was actually equal to 2 q double prime r naught rho Cp, okay, into u, okay. This was already pre-given, right. So, using that we are actually utilizing that to find out what are the scales of this particular factor is going to be, right, because the mean temperature gradient is also similar to the axial temperature gradient, right, because we are more concerned about, because dTm by dx is basically has taken care of only the radial part, axial part variation is still there. So, that is exactly what we have used in this particular scaling, okay, utilizing this, okay, which we already did earlier, okay. So, now that we have all these terms, okay, let us multiply all the terms by, so multiply by d square by delta t, right, all the terms, okay. So, the first term will become u by this q double prime rho Cp u d into d square by delta t, this is proportional to 1 comma 1 over x q double prime rho Cp u d into d square by delta t, right. That is the terms that we get, okay, right, okay. And we also know h is given as q double prime divided by delta t, right, okay. So, let us look at term by term once again, okay, using this definition. This is basically your heat transfer coefficient, okay. Based on this, based on the definition, you have h d by rho Cp into u proportional to 1 over x h d rho Cp u, okay, got it, okay. Now, if you look at this first term, this u and u gets cancelled with each other, okay, and you have alpha into rho Cp. What is alpha? Alpha is basically k by rho Cp, correct. So, the first term becomes h d by k, that is proportional to 1 or of the order 1, okay. This becomes h d by k into k by rho Cp, okay, into 1 over ux, this is the third term, right. So, this we already know that this is readily the definition of your Nusselt number, right, definition of your Nusselt number. This is h d plus some more terms that are situated over here. So, let us look at the nature of this particular term in general. So, this h d by k is the first term, alpha by u d is the second term, and then d by x is the third term, right. I have just written it in a more compact particular notation, right, okay. Now, we already know that d by x is a number which is less than 1, right, because x is the length scale. So, x would be normally more than d, right. We are talking about pipes like that, right. So, this term will be less than 1, we know that, right, this particular term only the one which I have circled, okay. Now, what about this term? We do not know anything about the nature of this term, like alpha by u d, right. Okay, the nature of alpha by u d is unknown, okay. But however, if we define a number called Pe, okay, which is called Peckley number, and we say that that is ud by alpha, okay, and if we say that that Peckley number is much greater than 1, right, that means alpha by ud should be much less than 1, right. In other words, this second term within the bracket will be much less than 1. In that particular case, what will happen, this entire term h d by k into alpha by u d into d by x, all of this term will be much less than 1, okay, or rather instead of saying much less than 1, much less than hd by k, which is the term on the left hand side. Or in other words, we can say that axial conduction is low or negligible. Got it? Okay. So, in other words, we are left with only the term involving the axial convection and the radial diffusion, or in other words, we are left with only hd by k proportional to 1, right. So, two important things that we have got out of this exercise. Okay. The first one, the most important thing is that hd by k is of the order 1. Okay. This means that Nusselt number is of the order 1. That means that Nusselt number in the fully developed regime is not a function of x or r, right, not a function, okay, and it is basically a constant, right. That is the first thing that we got. Okay. Let us look at what is the second thing. The second thing that we said, the most important thing that we said is that Peckley number is much greater than 1, or in other words, ud by alpha is much greater than 1. This is a new quantity that we have defined, right. So, what is Peckley number therefore? Okay, Peckley number is basically given by the rate of advection, right, divided by the rate of diffusion, right. Okay. So, this is what is Peckley number. So, that means high Peckley number means that the rate of advection is much more than the rate of diffusion, right. So, in the high Peckley number limit, okay, we can say, right, that okay, the axial conduction is very weak, right, compared to axial convection, right. That is exactly what Peckley number actually says. That means your rate of advection is so high compared to the rate of diffusion, right, that you can actually neglect the axial conduction effect, because it is a very small number in the high Peckley number limit. That means if your flow is very sluggish, say for example, that is barely creeping, okay, and this Peckley number much greater than 1 limit is not applicable, right, then what you cannot apply, you have to carry the axial conduction term with you, right. So, you cannot simplify this equation in this particular way, right. So, this is like an eye opener. We saw two very important things through this scaling argument. One is that axial conduction in most cases are negligible, because we are dealing with a convection problem with reasonably high Peckley number. That is always the case, okay, whatever flow that you are going to deal with, okay, because you have this factor u. Alpha is normally a very small quantity, right. So, if u is substantially large, this number will be probably substantially large than, I mean more than 1. But the most important finding was that based on these two limits, you have that your Nusselt number becomes a constant, okay. So, that means if you have to draw heuristically, that means if you look at this particular plot, and this is Nusselt number, this is x being the distance from the inlet of the pipe, right. Okay. Now, intuitively, as you know that so let us say that this is basically the developing region, and this is basically the developed region. So, we are basically looking at the Nusselt number in the fully developed region, right. Now, in the developing region, we all know that the boundary layer thickness is growing, right. It has not touched the middle of the pipe as of now. So, naturally, as you know, still that h is proportional to 1 over delta t. That means Nusselt number is also proportional to 1 over delta t, right. So, that means the Nusselt number value is going to be very high in the developing region of the pipe, right. So, if you talk about it like this, the Nusselt number value will probably come out as very high, but as this delta t goes on increasing, the Nusselt number value is coming down, right. So, in the limit it will become something like this, right. So, it is very high here and it is absolutely flat here, okay, and this value that you get is of the order 1, right. So, anywhere between 1 to 10, something like that, it will be your Nusselt number value regardless of whatever you do, right. So, it is very high initially, asymptotes and comes and becomes this flat line, okay, which is not a function of x anymore, okay, in the fully developed regime, right. So, that is a very important conclusion, that this is the region of high Nusselt number, this is the region of constant Nusselt number or a heat transfer coefficient. Okay. So, this particular finding is one of the most important thing which you did not get in a flat plate boundary layer, right. Okay. There the Nusselt number was still a function of Reynolds number raised to the power of half, if you recall, right. So, here of course, the Nusselt number no longer remains a function of your x anymore, okay, which is one of the most crucial findings that you have. Okay. So, now what we are going to do, now that we have established the full fledged equation, right. Now, the next half of the business will be to determine what will be the temperature profile. We still have not done anything to the temperature profile. All we have done is that we have made a couple of very interesting observations. We have reduced the energy equation to a very nominal form by neglecting most of the terms. Okay. So, there are three purpose things that we achieved. We reduced the energy equation, okay. We saw that in that limit Nusselt number becomes equal to 1, and we saw that of course axial the Peclet, this is a limit, this analysis is only valid for high enough Peclet number, right. So, if Peclet number is low, then you cannot apply this particular limit anymore, right. Okay. So, let us look at the first energy equation, okay, and let us look at what we can do with it. Okay. So, energy equation now in its revised form is u by alpha dt by dr, sorry, writing too close to the, okay, u by alpha dt by dr is equal to okay. So, that is the first thing, and once again this equation now you see is devoid of the axial conduction term, right. So, once again fully developed u comma t, okay, the interest, so x is greater than xh comma xt, that means we are in a region which is far away, and of course we got that Nusselt number is of the order 1. Okay. Now, let us look at how can we define a temperature profile in the fully developed regime, right, which will be a function of r. Like in your velocity profile, we had velocity was a function of r only. Temperature is not that simple because t is a function of x comma r, but can we do some variations on this t so that it becomes a function of both r only with respect to r, right, but normal t is a function of x and r. Okay. So, let us take the definition of Nusselt number, the primitive definition, okay, it is r equal to r naught, okay, that means at the wall T by T m, okay, this is of the order 1, right. Okay. So, that would mean there is a d over here, okay, that would mean that dt by dr r equal to r naught is the same as T naught minus T min, right, for any x, right. Remember that T naught and Tm both can be functions of x only, right, because the wall temperature and the mean temperature both are functions of x, because mean temperature by definition you have removed the variation with respect to r, right. So, on the left hand side whatever it is, on the right hand side whatever it is, okay, for any particular x this relationship is valid, right. So, therefore, we can argue that the x variation of dt by dr at r equal to r naught, right, is same as T naught minus T naught minus T mean, isn't that so? Because otherwise for any x it won't be acceptable, right. So, for any x this relationship is valid, that means the variations on both sides must be the same function of x, right. So that they kind of cancel each other out, right. Yeah. So now we can have an important, so based on this, okay, based on this particular definition, okay, but t is normally, but when you define dt by dr, say for example, right. So dt by dr is basically nothing but the variation of the radial temperature profile. Now when you look at dt by dr, what do you think that dt by dr's function is going to be, right. So dt by dr is a quantity, okay, dt by dr at r equal to r naught, that means you are specifying it at a particular thing that has an x variation, right, but that x variation is basically taken care of by whatever is the t naught minus t mean variation is, right. Okay. So if I kind of conjure this up, that dt by dr by t naught minus t mean, right, what will be the definition, what will be the variation of this quantity, okay, because this quantity therefore, okay, the upper quantity is a function of both x and r, the lower quantity is a function of x only, okay. We know that when you evaluate it at any particular location for any r, okay, it kind of shows the same kind of variation, right. So is there a possibility of writing this particular equation, using this particular equation, right, and stating that this is going to be a function of r only, okay, that is what our main objective is. So we will stop here, okay. In the next class what we will see is that we will find out that how we can conjure up, okay, a definition for the temperature field, okay, a definition for the temperature field which is a function of r only, okay. So see you next class. So last class what we saw was that dt by dr evaluated at r equal to r naught divided by t naught minus t m is basically a constant, okay, basically a constant and not a function of r, right, not a function of r, not a function of x, okay. But we know that dt by dr by definition, right, is a function of both x and r. So one can conjecture that perhaps dt by dr by t naught minus t mean will be like a function of r only, okay, because t naught minus t m is a function of x. So dt by dr, we evaluated it at one particular point, we saw that it was not a function of both were same functions of x. So therefore once you divide one by the other, there is a possibility that we can argue that this will be a function of r only, okay. So based on this definition, okay, let us define what will be the temperature profile. So temperature profile will be t naught minus t divided by t naught minus t mean, okay. This is a function of r only, okay, whereas however individually these are functions of x, t is a function of both x comma r, okay, t naught can also be a function of x, got it. But even though whatever be the nature, right, together this is only a function of r, got it. So together it is a function of r only, okay. So this will be the definition of temperature in the fully developed regime, right. So in the fully developed regime this will be the definition of temperature that we are going to use, okay. Now let us take the very basic definition, okay, that before we go into all these things, okay, we can take the basic definition now, that let us see what can be, what are the different kinds of temperature profiles that we can actually have, okay. So one will be of course the uniform heat flux case and one will be the uniform wall temperature case, okay. So we will look at both the uniform wall temperature and the uniform heat flux both, okay, in the subsequent section. So let us take the uniform heat flux event over here, okay, because that is a little easier to start with. Uniform heat flux, that means the boundary condition has changed basically. So this is the pipe once again that you have, goes through, so there is a heat flux. This is Q double prime, this is basically R naught that you have, okay. So this is a fully developed temperature profile that we have to find out. Q double prime is basically a constant, This is a uniform heat flux case, right? Got it? Okay. So we have said nothing about the wall temperature. Here the wall temperature is not a constant. Okay, wall temperature is still given by T naught, but it's not a constant, right? So that we will see what that wall temperature is. So instead of defining the temperature in that way, let us first say Tx comma R, T naught x. I am writing the functional variation so that you can get an idea. H F R over R naught. That is the definition that we have applied, right? This is a very simple enough definition once again, because T naught minus Tm has been basically substituted by Q double prime. That is all, and using the definition of H, right? So if you recall the definition of H, what is was Q double prime divided by T naught minus T mean, right? Okay, so if you have to substitute T naught minus T mean, it will be Q double prime divided by H. That is exactly what we have done over here, this particular term, right? This is, there is no difference between this and this. They are essentially the same. Only T naught minus Tm has been substituted by Q double prime, because Q double prime is a given and it is a constant. Okay, that's the only reason, okay, that we have used. So don't lose the track of this particular thing, okay? So therefore, dt by dx, right, should be equal to dt naught by dx. When you differentiate it with respect to x, your q double prime is a constant. This function is a function of r only. So when you are differentiating by x, the second term just vanishes, right? So this is the first quantity that you get, right? Okay. Now again, we also know that Nusselt number is of the order 1, correct? Okay, so therefore q double prime into d divided by k T naught minus T mean is of the order 1, right? Okay, of the order 1. So therefore, okay, therefore from this particular case, okay, if this is of the order 1, then what can we say? Or dt naught by dx is the same as dtm by dx. If you just take it to the other side and again differentiate it with respect to x, you know q double prime is a constant, so it becomes dt naught is equal to dtm by dx, right? So compositely what we get from this is your 2. So combining 1 and 2, what do we get? We get dtx, right, partial is equal to dt naught by dx, that is equal to dtm into dx. Got it? Okay, so all the slopes are basically kind of the same, right? Now in addition to this, we already know that dtm by dx is basically 2 by r naught q double prime divided by rho cp into u, right? Okay, this we already know. Recall, this is the average axial velocity. Got it? Got it? Okay. Now this is basically therefore a constant, right? Because your q double prime is a constant, u is the average axial velocity, which is a constant, okay, and everything else is a constant over here. So therefore, as we wrote earlier, dt by dx equal to dt naught by dx equal to dtm by dx is equal to a constant, right? This implies that this is a constant as well, right? dt by dx is a constant. So temperature, this implies that temperature at any r varies linearly with x. Temperature at any r location varies linearly with x. So therefore, why not take a look at the sample profiles? Okay, so let us take, this is the tube. Okay, so let us take, this is one section, this is another section. These are all in the fully developed regimes. Pull these things down. This is your x1, this is your x2, right? So the temperature profile is the mean temperature. This is the profile of the mean, this is the full temperature profile. Mean temperature will be somehow here, right? That will be the mean temperature, right? So at a different cross section, you will have that there will be some variation, right? Okay, and the mean temperature will be somewhat like that, Tm at that particular location. So if you now plot the variation of the mean temperature, you will find that your mean temperature goes up. Okay, so this is your mean temperature profile, right? The wall temperature, okay, as you can see from that, is also going to go up. Again, linearly, the slope is the same, right? So it is also the wall temperature is also goes up. So it is a linear, both are linear, right? So the wall temperature goes up linearly, the mean temperature also goes up linearly. Now as you can see, that T naught is definitely more than Tm. That's why we have one over the other, because that is a wall. Wall is the maximum temperature over here, right? Maximum temperature over here. So it will be naturally more than the mean temperature, okay, because of the curvature. You can see the curvature over here, and you can easily make out that the wall temperature will be the highest. This is basically T naught, this is basically Tm, if there is any ambiguity. Okay, so that is the wall temperature and the mean temperature. Okay, so between any two locations x1 and x2, you will see all of them going up like that. Okay, so therefore we have established that in the case of a uniform heat flux, these two follows like two parallel lines kind of thing, right? So the wall temperature also increases, Tm also increases, right? Okay, now let us look at the situation that how this can be now solved in a proper fashion. Okay, so again the equation is still the same, that dt by dx is equal to d square T by dr square plus 1 over r dt by dr, right? U we already know is given by 2u into 1 minus r by r naught square, where u is basically given by 8 mu dp by dx. Got it? Okay. So that is the original thing that we said. This was the average velocity that we said, okay, and this was the whole profile of the velocity, right? Also the temperature profile we also defined, that was equal to T naught minus q double prime by h f into f by r naught, right? So that was the two definitions that we had, right? And r bar is basically can be taken as r over r naught in the normalized variable. Okay, so based on these quantities, right, okay, we can now substitute them back in the energy equation. So it becomes u by 1 by r bar square into 2 into q double prime divided by r naught rho Cp into u. Why can I substitute that? Because dt by dx, this is because dt by dx is the same as dtm into dx, right? That is a substitution that we have made, minus q double prime h into f double prime, right, plus 1 by r bar q double prime by h f prime, okay, where h is given as q double prime divided by T naught by T mean, right. So this is the very standard equation, okay, or in other words, now we can write it as 4 q double prime 1 minus r bar square divided by r naught into k is equal to minus T naught minus Tm into f double prime minus 1 by r T naught minus Tm into f bar. Okay. Now all this f prime is basically given as df by dr, so you can convert them to the corresponding dr bar coordinate system. So that is fairly easy to do. Okay, and you can also introduce Nusselt number in the mix, because Nusselt number is given by, as you know, h d by k. Okay, so based on that, okay, what we can do is we can write the full equation now. Okay, so I will do one more step so that you get a feel. Or d square f dr bar square plus 1 over r bar df by dr bar 2 hd by k into 1 minus r bar square, right? So this can be further written as minus 2 into Nusselt number into 1 minus. Okay. So I have skipped a few steps, but you can easily follow that what all we have done is converted it to the r bar coordinate system, right? Okay. Now let us solve this particular equation then. So d by r bar or df by dr bar is equal to 0 at r bar equal to 0, right? Okay, so this leads to C1 is equal to 0, or df by dr bar minus 2 Nusselt number r by 2 plus 2 Nusselt number r cube by 4. Integrate it one more time. F is equal to Nusselt number into r square by actually this will become 2 now, okay, plus Nusselt number r to the power of 4 by 8 plus C2, right? Okay, now F, as we know, is T naught by T divided by Q double prime by H. Okay, so and H of course we know, so F will be equal to 0 at r bar is equal to 1, right, because it will be the wall at that particular point. So therefore C2 will be equal to, okay, half minus 1 by 8 will be equal to Nusselt number 3 by 8. So therefore the total form of F will be Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8, right? So that will be the total expression that we will get, okay, for F, okay, because F is the thing that we have to solve, okay, utilizing the boundary conditions that we just now mentioned, right, that F prime is equal to F equal to 0 at r bar equal to 1. Okay, now that we have it, okay, now let us write the full equation. Therefore your T is given as T naught minus T mean into Nusselt number 3 by 8 r square by 2 plus r to the power of 4 by 8, right. So this is the, if you consider F, if you open up F, so that is what you get, right. So from F, basically from F definition, right. So that is what you are going to get, okay. Now, so of course you can take things, so this T is basically a function of both x comma r, right. Now my original definition of Tm, if you recall, was 1 over r naught into u divided by this was 2 pi to r naught T naught minus T u r dr d theta, okay, right. Do you recall? So that was the original definition of Tm when we actually did it. Okay, so therefore T naught minus Tm will now, if you can put the terms in within the bracket. Okay, so that means you can integrate out this thing in a little bit of a better way. Okay, 2u1 minus r bar square r into 2 pi dr, right? That is the equation. So this will give you 4 into 0 to 1 T naught minus T 1 minus r bar square r bar dr bar, right? That is the expression that you will get. Okay. So therefore we have basically two terms. Okay, one is this, okay, which basically gives you T minus T naught is equal to this. Okay, the other one is T naught minus Tm is given as a function of this, right, if you look at it. Okay, so therefore what we are going to do now is that we are going to take this definition and substitute it here. Okay, so T naught minus T, we are going to substitute it in terms of T naught minus Tm, okay, in this expression. So T naught minus Tm is equal to 4 into 0 comma 0 to 1, again T naught minus Tm, we are substituting it now with the Nusselt number 3 by 8 r square by 2 r to the power of 4 by 8 into 1 minus r bar square r dr bar, right? Okay, so that is the substitution, right? So now this gets cancelled, that is because T naught or Tm is not a function of r anymore, so that you can take it out of the integral. Okay, so what you are going to get is 1/4 is equal to 0 to 1 Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8 into 1 minus r bar square r bar dr bar. Or you take the Nusselt number out because it is a constant by definition, so the rest of the integration becomes easy. It's basically an integration with respect to r. Okay, so if you do this integration, do it, you will get 48 by 11, which is 4.36. That will be the answer. This is of the order 1. So our scaling analysis was correct. The exact value is 4.36, okay, which has come out through this exercise that we followed. So two things we did. Fr represents what we call the temperature, the fully developed temperature, right? Temperature, right? That we have found out what the fully developed temperature was. If I have to write it once again, you just note this thing down, because these are the findings, like fact findings, is given as Nusselt number 3 by 8 minus r square by 2 plus r to the power of 4 by 8, right? And what was f? If you recall, what was f? F was basically T naught minus T by T naught minus Tm, or it can be also written as T naught minus T divided by Q double prime by H, whatever it is, right? So this is the definition. Second finding is, or that is what we found, that Nusselt number was 4.36. So essentially you can say f is equal to 4.36 into 3 by 8 minus r to the power of 2 r to the power of 4 by 8, okay, is what is your definition of the temperature profile. Okay, this is all for uniform heat flux case. Okay, so this is like the corollary, okay, of this particular thing, right? We also found out that the Nusselt number, so we have found out the exact variation. So this Nusselt number is of the order 1, as we decided earlier. Okay, we have found out what is the definition of x going to be. Okay, similarly we also found out another important thing, that dTm by dx is the same as dt by dx, right, is the same as dt naught by dx, right? So we said that all the these two temperatures, well, I have not drawn it exactly parallel. this will be T naught, this will be Tm. So both of these temperatures varies linearly with x, okay, linear functions of x, and this is equal to a constant, linear functions of x, which was a surprisingly interesting tool which gave us this particular thing. Okay. You can also find out what is going to be your mean temperature now, because you have already got the definition of mean temperature. So, you can find out what is your mean temperature profile is also going to be. But utilizing all these things, we have got these three important correlations, or these three important findings out of this entire exercise, right. Okay. So, this is vitally important, because next we are going to look at the uniform wall temperature case. So, this was the uniform heat flux case, and we saw that this is how the temperature profiles vary, this is how the Nusselt number value will be, and this is how the temperatures, the different temperature gradients are related. So, these are the main three. So, this is like a summary that these are the main three events that you should be really bothered about, okay, when you move on to the next. Okay. So, uniform wall temperature, we will start, pose the problem and finish it afterwards. So, uniform wall temperature, okay, this is a very similar thing now, except now that the walls are fixed at a temperature of T naught. Okay. So, T naught is basically a constant, right. Okay. T naught is basically a constant, okay, and your dTm by dx is still given by the same thing, q double prime rho Cp into u, okay, and q double prime is basically h into T naught minus Tm into x, right. Okay. So, now so using these two parameters and using our definition that what it can be, okay, we will see in the next class that how this heat transfer for this particular system can be analyzed. Everything else is the same, except that the heat flux is unknown over here, only the wall temperature is known. This is applicable regardless, the dTm by dx, and this is also applicable regardless. Okay. All of this can be written in that same fashion, right, but except we do not know what is the value of this q double prime going to be, but we know what is T naught, it is a given to us. So, we will see that how this particular problem pans out in the next class. So, we will finish the uniform wall temperature case and we will see where we get to that. Okay. Thanks.